apart from us too. So can we start now, ma'am? I think we
Yeah,
have
yeah,
enough,
we
right?
can start. Yeah,
Okay. Okay. So let me share my desktop. Let me see if I can share. Select screen to. Okay. So can you all confirm that you can see my screen? You should
yeah.
see a blank screen. Okay, cool. So today, last class, what we you can all see my screen, right? So last class, what we covered was the basics, introduction of Docker, and we did some exercises. Uh, do you guys have any questions on the last class? If you have any questions, we can take them uh, and move on. You understood what is Dockers, why do we need Docker, how containers are initialized, what are the container lifecycle, all those things are clear, concepts are clear. Anyone? Okay. Thank you. Please just for your um, yeah. So um, So let's today cover Docker storage. And what we'll cover in today's agenda is we'll just quick brush up of the basics. So if you have your, I presume most of you have your Docker console in front of you, able, either your laptops or however, and you are able to run some of these Docker commands. So I'll be running through a set of commands that we tried out last class, and we will, then move on to understanding what are volumes, what are Linux, how Linux configures volumes. And this is important for us to learn because today's world, everything is virtual, everything has to happen hot swappable. If you want to expand your storage, it has to be happen without any downtime. Everything is like online, right? So we need to understand how those are organized. Then we look at overlay and a bit about Docker file system. We covered a bit of overlay file system in the introduction, where we saw that we made some changes in the diff, the diff and the merge layers of your file system. And we saw how we briefly discussed how overlay file systems have a, a read-only part and a read-write part. And I briefly touched upon how the delta is delivered in a when a container is updated, how a delta is delivered in the Docker file system. We'll dig a bit more into that, and then we'll understand how Docker uses storage and how we can persist storage across the container lifecycle. So what we looked at in some of the examples that we did last time was that when we did when we made some changes to a running container, and when we killed that container without saving those changes, the changes were lost. And we also saw that when the container was the container was removed or deleted or killed, then the files that were created on the during the life cycle of the container that we were able to trace on the underlying host also got deleted. So we also found ways to persist that, but that is not feasible in a production environments, and we'll explore some of the different ways in which Docker volumes are used, and we'll move on to hands-on. So after that, we will cover about Docker networking, uh, depending on the time. Okay, depending on how much time we have, I will try to cover about Docker networking today as well. If not, then we will schedule one more class, and we will. It's probably better to schedule one more class because then it will become too much information overload. Okay, Docker networking is a bit slightly tricky. We'll need to understand. We'll spend more time on that. So let's see how it goes. With me so far? Okay. So with that we'll just go to some of these basics. Okay. So I have my you know the my virtual machine here, and I have my Docker running on this. Okay. Let me increase the size. Increase font size. I guess this is visible, right, for all of you. So you have to tell me if you can follow what is going on the screen, what you or if you cannot, you know, see what I'm typing. So first thing we did was we ran Docker Hello World. We are all clear with that, and we understood the commands around Docker pull and Docker images. So Docker pull is a command that is used to pull a certain image. Um, you know. Um, uh, that many times gets done as a prerequisite step when you do a Docker run. We observe that as well. So here you can see when I say Docker images, I have all these images with me. And if I want to run any of those, it runs it from the local repository where it has downloaded. But if I try to find anything that is not here, then basically we will try to uh, it will try to run that download that image from the Docker hub, and then you know execute that. So we can just try a quick. So let me remove this image, hello world. So now I can remove it either with the hello world or with the image ID. Okay, so let me remove that with the image ID, and it is removed, and you can see that there's no longer hello world. So now when I can say docker pull hello dash world, this is the command that will try to pull the default tag. Now what happens is when you see this tag, right? So this is, in general, when you're playing around with it, it will always be the latest. And if you remember in yesterday's class, in the previous class, I mean, we also discussed that one of the things your containers infrastructure allows you to do is run multiple versions of the same application on the same host. So when you have that, then this tag will contain the actual version that you really want to use. So that is how it works. So here we have downloaded this Docker, and now you can do a Docker images, and you can see the hello world is downloaded again. And you can run it as usual. Uh, and it will run, and it will give you this output. So if you don't have, we observed that it says not did not find the image in the local repository. And then I'll just say for example, I'll just do this. So it says, you can see, right, I can't find the image locally, and there is no image called foobar, which says you cannot access it. It does not require, right? So these are public access. The Hello World and a lot of other are publicly accessible, so they don't need any access. But this might not be there, or you can assume that this image is not here in this case. Okay, that's the error. So essentially, this is how Docker pull and thing works. So we looked at Docker images, and we ran the Docker Ubuntu. We learned what are the meaning of these IDT. So you can, if you want to see that, so you can run the help, and you can see what is the meaning of each of these options. So you can see here that -I makes it interactive, right? So keep the stdin open, even if not attached. And you can see what -D means, to run it in a detached mode. Okay, run the container and print the container ID. and T means allocate a sudo terminal to this container. Okay, so when you run this command using docker run minus idt ubuntu bash, this is what we did: install the vi and we did a docker commit, right? So you can see that you can run with the command minus idt. You can run this ubuntu, and then you can look at what other images we have. This was the one that we created. You can see 6 days ago, it clearly says. And one second. Yeah. So we have this another image. We last class, if you remember, we installed VI inside Ubuntu and we created this image. So now we can say um, now we can say docker run minus idt, and we can say Ubuntu with VI, or you can give the image ID. You can just see how both it works. So I explained to you the concept, right? Both name and ID concept I have explained. So you can now see Docker PS, and you can see that these two images are up and running. So now if you log in, you will see that this particular, you can see, right, the image it is giving you, if you give the ID, it is giving you that. So now if you log into this Ubuntu image, then you will see that there is no VI. And if you log into this particular image, you will see that it has VI installed on it. So let's just quickly check that. And for that, we said we will use the docker exec minus IT. So if you want to see the what minus I and minus T means, you do a minus minus help and you will get the options. Minus I means make it interactive. Minus T basically means you allocate a TTY. And you don't want to make it detached because you want to log in into that. Okay, so we'll say docker exec. So we need the reference to the container. So we do a docker ps. And now we log into this first container, docker exec minus IT. We'll just say, you can see again, right? We can go either by name or string, and we say bash, and you now have a console. You can see, right? You are inside this container ID. You can see, right? Root at the same ID it is giving you the prompt. So now if you say vi, it says command not found, not found. So now you exit from this and you use the same command, but this time you log into the other container, right? Take the container ID and then you give it bash. So in this case, you can see if you have VI, you have installed VI. Okay, so clear, right? So please feel free to stop me if you have something in the middle. Okay, because I'm just revising the exercises that we did in the last class, and if you want, you can revise that as well. Are you following the commands? If you want me to type the commands in the chat window, I can do that as well, but I think it's quite straightforward. You can try it out. With me so far?
Yes, sir.
Yeah. And we will do these exercises when we go, other exercises when we go to the um, networking class, where we look at the port bindings and all those things. So this one we will take it up in that class, so we'll skip that for now. Now this is a dangerous command. This is like this command you can keep it actually to, one second, let me see if I can open the chat. There's a chat window. Let's see. Okay, so I'm typing on the chat window. So this is a slightly, tricky command. So be careful when using it. This like your RM minus RF. Okay, it will delete everything. So I'll show you how this works. So if you say docker ps minus a, it shows, okay, we are inside the container. So now we say docker ps minus a, it shows all the containers. Okay. So now it shows all the containers. Now if I say minus qa, you can look up the command help options. It will only print the container IDs. It's not printing header, it's not printing other detail, it's only printing the container IDs. Now when I say docker rm minus f, I can do it one by one, right? Or I can type this, right? Now this will delete two containers. Okay, now it has deleted two containers. Now when I say psqa, you can see those two are deleted. Otherwise, I can take the output of this command and pass it as input to this rm minus f in a shell command. So that is what I am doing here. I am taking this as input, right? It has the same effect when I do this, right? You can see, right? It is typing the output here. Now instead of echo, if I pass this to docker rm minus f, now you see it has deleted all the other commands, and when you see there are no running containers. Okay, so you keep this command when you are experimenting. Eventually, when you keep creating and deleting containers, removing or containers, there will be suddenly a big backlog of containers that builds up. And if you want to clean up your Docker engine, you can and use this command. Okay, just exercise caution when you are running this, because it will delete all instances of containers. Any questions? Any particular command you would like to try? You did not understand. You had some questions about from the last class. You can type in the chat also if you are not comfortable talking. Guys, come on. Somebody has to say something, otherwise I'll not know even if I'm online or if I'm just talking to myself. So please respond, okay? Yeah, it's clear, right? From what we had last class. These were the
Yes, sir.
comments that we learned. Okay, good. Thank you. So let's move on with that. Let's move on to the Docker storage part, okay, Docker volumes part, wherein we'll try to understand how, you know, the basics of how Docker works with storage or disk storage. We discussed, right? There are multiple resources, CPU, memory, and other things, and we'll try that out. So with this, let me just show this. So this is mostly about Linux kind of like volumes. Okay. So what happens with the Linux volumes is, if anybody familiar with how file systems are created on a computer? Anybody has tried out installing a new disk and formatting it, creating partitions? Anyone familiar with that? Okay, so essentially what happens is, you see, right, if you look at your laptop or if you look at a Linux machine or anything, you will see that your um, um, your disk, the physical disk that you copy or attach in your laptop, there are multiple layers of abstractions, that are software abstractions, that are built on top of it before you can access it as and write to it as a file system. So the first multiple levels include, the first level is partitioning, right? I'm pretty sure most of you will be familiar with what is a partition. So you take your hard disk and you partition that into two, physically partition that into two disks. Essentially, what is happening, your disk has a structure called the master boot record. Okay. Anyone familiar with this? Have you heard of this term? master boot record. Okay, so master boot record is basically your file system table. Okay, have you studied file systems in your computer system course yet? Computer science course yet? Okay, you probably would not have. It will be a small part of your this thing. So file system basically is an index of how blocks are organized on your disk. So a disk, if you really see, contains what? Disk contains blocks, correct? Ultimately it starts from the magnetic 0 1 bit, if you are going with a magnetic disk. And essentially what happens is it becomes an abstractions that you build on top of it, how you organize the data, how you write to it, how you retrieve it, right? So that's basically about your storage. So essentially what happens is, if you have it's inefficient to write every single bits or even bytes. So your disk's IO, or the disk input output, happens in terms of blocks. Okay, so blocks are basically nothing but an organization or a set of bytes. Typically, block size, will be. Let me see. What should be your typical block size? I think it's either 512 KB, or probably now it has increased to 1 MB or 2 MB or more. So file system block size typically will be, it can range from anywhere between, you know 4 KB to 64 KB is what, you know I think so. So you can have different sizes, but I guess typically it will be around, let's assume it will be around 4 to 64 KB, right? 4 to 64 KB default size. Okay, so that means when a data is read from a disk at a time, you read it in chunks of this, and when you write to it, you write it in chunks of this. So you can see, right, depending on how your write patterns emerge, you have to set the block size. Now if you have a generic file system and your file sizes are very small, then setting it to 64 KB means that even if your file size is like, let's say, 10 KB, it will occupy minimum 64 KB on the disk. So we need to be careful when designing the block size and formatting these are all options when you format your disk. So you can create that. So now blocks are organized into sectors. Okay, so essentially this is establishing, now that you have established that the block is what is accessed in one IO read command. Now you have to establish proximity, right? Spatial organization of your data. So there you have to understand that there are two primary things when it comes to, nowadays things have changed because we all use solid state disks where everything is accessed by the same latency. Essentially you have to understand that historically, um, many of our disks were all magnetic disks. So how many of you have laptops that still have magnetic disks, hard disks, and not SSDs? Just a show of hands, a few of them, if you know. Yeah. So if you understand how a magnetic disk works, magnetic disk has eight, your hard disk will have eight disks stacked on top of each other, rotating on a central spindle. Okay, so you imagine this as eight disks that are spinning at the same time. Okay, depending along the same axis, which is called a spindle. Now your data, your sectors, data in a disk basically is written in tracks, concentric tracks on the magnetic disk. So this, within tracks, a section of the tracks, a track is a sector. Okay, this is how the disk is organized. Now your IO happens through a set of eight read write heads that simultaneously access data from each of those eight individual disks. So when you are accessing data in such a scheme, what you have to understand is you have two aspects, two dimensional motions, two two different, not in two dimensional, the to access a particular block of data, the disk has to be moved in two different motions. So the first one is what we call the seek. Okay. So what it means is your file system table contains data about where a certain block of data is stored, which is which includes the track sector and block number. Now, when you say that it is stored in track 1, 2, 3, 4, or I mean, I don't know how many tracks will be there by default, but let's say track N, then your read write head has to move on the radial axis of the disk to position itself to the right track. So once it positions itself to the right track, the disk has to spin. The disk has to spin for the read write head to reach the position where the block is actually stored. Now, this is called latency. The time it takes for your read write head to position itself on the right track is called seek time. Okay. And the time it takes for the disk to spin and the right block to to be located under the read write head is called the latency. Now, most of your file system algorithms are designed around optimizing seek time and latency time. So there are different file systems depending on the specific nuances or the use cases or the applications of what is stored on the file system and how data is stored and retrieved. Basically, that file system will optimize certain algorithms. Now, here, what we have to see is, I'm typing these things on the chat. Okay. So what we need to notice is now there is a concept of what is called a cylinder, for example, right? Now, what is a cylinder? So we imagine it's a virtually I have to imagine this. We have now 8 disks lined on top, exactly on top of each other, with data being stored in concentric tracks on each of these disks. Now, imagine a certain track number on the same track number on all the disks. This is called a cylinder. This structure is called a cylinder. Now, why is this important? Because if I am accessing, let's say, 4 MB of data and that is stored on different tracks on different disks, now it becomes for each to me to access that 4 MB of data, I have to sequentially keep positioning my read write head on different tracks. So each of that is a seek time. It is adding to the seek time. But instead of that, if I store all the related chains of data or blocks of data on the same cylinder, now I only have to seek once. You say that seek to this cylinder that is seeking to that particular track position, and from there it is only the latency I have to worry about. Okay. So it is only about ensuring that how much each disk has to spin for that read write head to be positioned on the right set of blocks so that a simultaneous read can happen is now the problem. So now we are optimizing the seek time by organizing data in cylinders. Okay. Have you heard of this term cylinder in the hard disk organization? If you have done any partitioning or those kind of activities, you would have heard. Okay. So you can imagine, right? This is how a cylinder works. Now, these are slightly kind of archaic notions. Now, this is what innovation is. Okay. This is what technology evolution is. Now, most of our disks are solid state disks. Okay. You're familiar, right? We have SSDs. Now, since you have solid state disks, what they ensure, right? It's electronically stored. The data is not stored on magnetic disks, but it is stored on rather electronic chips. It's stored on electronically organized data. Now, the thing with electronically organized data is it's stored in a matrix. And what it allows you to do is it does away with your seek time and latency time. So now you have ensured that there is no relationship between the positioning of your data and the time it takes to retrieve it. Now, this is a big evolution step because what is happening is you are removing the big constraint of seek time and latency time. That's why you will observe that laptops that have solid state disks boot up extremely fast. They're extremely fast, and laptops that run on hard disks become extremely so. So when you are buying laptops, don't buy laptops that have 5,400 RPM. Buy laptops that have at least 7,500 RPM. Why? Because 7,500 RPM is almost 50% more than 5,400 RPM, which means that your seek time and latency times will be significantly reduced, and the hard disk will functions, and your operating system will function more efficiently. So now you understand, right? So when you're buying a laptop, don't buy a laptop that has 5,400 RPM hard disk, because it will be lower cost, but then you will not be able to function on it. But then you either buy 7,500 RPM, or I don't know if any laptop hard disks are available with 10,000 RPM. If they are, then you should buy that. Or best case is buy a solid state drive, SSDs. Okay. So this is how hard disk physical blocks are organized. So now what happens is, you can see, right? This is your hard disk. It is, once you configure a hard disk, now there are two ways to create file systems. So once you have a disk, you can create partitions on the disk, and you can format that partition, and you can create a file system on top of it. So formatting a partition is a process that organizes the blocks, that traverses and identifies each of the block sector and cylinder numbers, and records it in your file system master boot record. Okay, to say that this is the expanse of this file system, and this is the layout of your blocks on the disk, on the physical disk. That is essentially what is your formatting process. Now the downside of formatting process is, if you are partitioned your disk to, let's say, 200 GB, then it is fixed. You cannot you can expand that, but of course if you have enough storage, but it will be slightly disruptive. If you reduce it, it will go. So this is always a problem, it is not flexible. But instead of that, you imagine there is a software in between which organizes these blocks, and that can, you know serve these blocks to the file system drivers. Then it becomes easy for you to expand your drives without impacting the functioning of your existing file system. So that is called your volume group. Okay. So what you do for a volume group is, you can see, right, there are physical volumes here. In this, there are three hard disks in this machine, and each hard disk is partitioned into six partitions of 32 MB each, and they are physical volumes. And now you can group these physical volumes together to form logical volumes. Okay, so here you can see that this particular logical volume has four blocks. There are four physical, you know, volumes from H disk 1 and one from H disk 2. And on top of that, there is a journaling file system. And now there is one partition from one logical volume that contains one physical volume from H disk 2, which is formatted with a ext3 file system. And then another one which has two physical partitions or physical volumes from HDIS3, which is formatted on a JFS2. Okay. And you can see that they are mounted on these points. You are familiar with mount point concept, right? So you go to your machine and run the mount command on your Linux machine, then it will tell you what are the mounted file systems. Okay. So here you can see that these are physical partitions. This bunch of physical partitions form a physical volume, and then you create your logical volumes, file systems, and mount point. So this is mounted on slash home. This is mounted on slash var slash World Wide Web www, and there's a slash data. So this is how a file system is typically organized. Okay, with me so far? Okay, so now let's switch gears and try to see if our system has those LVM concepts. So let's see, try this. Let's try this. So you can see this, right? This is my machine. This is my file system. Let's look at each of these organizations. So let's start with physical volume. We'll say PV display. What? PV display minus all. Okay, PV display, let's say minus V, doesn't show. LV not sure how this is organized, so this is not showing anything. So here, let us look at LV, LVM, LV create, LV display. So LVM is not configured in this. Looks like. Let's look if it has any VG volume groups. So VG import, VGS, VG scan, uh, VGS, right? No, there are no volume groups configured in this. But when you do have, this is where you would actually. This is a cloud VM, so probably it is not having any any of these configurations. But yeah, this is how you would go about looking into that. Okay, so let's go back to this. Let's move to the next one. So let's look at analyzing some of these Dockers again. Okay, so we tried this, right? We tried this exercise already, right? And one more thing we can try is how do we, let's look at one more command today we can run, which is Docker inspect. Okay, so let us do a Docker PS. So we don't have anything running. So let's look at running some container, right? This is running my one this thing, and I can run my. Now you need to understand one command called Docker inspect. Okay, now Docker inspect allows you to inspect Docker resources so that you can be, it can be anything, right? So for example, I can say Docker images, and we created this image, right? We took the Ubuntu image, we added installed VI in that, and we created this. So you can do a Docker inspect, and you can run this command. So now it will tell you a bunch of information about this particular command. So now it's telling you, what is this telling you? This is a, what is a report tag, right? And what is the parent of this? And what is the container that is currently running this? You can see, right? If you saw when I executed this one, it is giving me this container, right? Is that the one that it is telling me? No, it is a different one. It is telling me. Interesting. We'll look into that. So here is the containers that is running. And you can see what is the Docker version that was used to create this image. And you can look at these directories, right? So you can look at what are the rootfs layers inside this and what are the file systems, lower direct merge directory, upper and work directory. Okay. So these are all the structures of your this thing. So if you actually go, you should be able to track. So now let us see, we do a containers, right? We ran the containers. We can inspect what's happening with the containers. Docker inspect, and you can look at this particular image, and then you will see what it is telling you. It's telling you multiple things, and it's telling you what is the command used to run that, right? What is the status of it? What is the PID of this on the host? So this is the PID of your Docker container on the host. Okay, not inside the container. Now it's telling you the image which is running this. It is telling you all your resolve.conf system configuration paths, etc host name, all those files. And then it's telling you the name of this. And you can see, right, what is the driver that is running it, what is the network configuration, what is the configuration of the host, all that specific details will be available with this particular this thing, right? So you can see here, right? CPU quotas, everything. We have not set any quota. Remember, we spoke about C groups, right? So we have not configured any quotas for this or limits for this. So currently everything is set to 0. So now you can see what are the mounts and configs and etc. Right? Network settings, all those things. So this can be done for every configuration item that you create. Okay. So now let us look at what do we mean by this upper directory, lower directory, and all those things. Whatever we saw with this image, Docker image, right? So we saw here, right? This is my data of my overlay 2 file system. So let's look at what the overlay file system is and how it is used in Docker. So essentially, you will have a lower directory, upper directory, and a merged directory. Now, lower directory is a read-only directory. Upper directory is a read-write layer, and then the merged directory is your what is presented as the final, what is the mount point that appears on the host in the user. With me so far? So essentially, how does it map to your Docker constructs? So in the Docker, we saw the image layer. Okay. So sorry. In the Docker, okay, some pointer. So in the Docker, we have the image layer that maps to your lower dir. Now this is the read-only layer of your container. Okay, in the Docker file system. Now, when you launch a container, it creates a container layer. Okay, and that is what you will see actually. Now, then the container mount is what actually you use it, what the user uses. Now, how does this work? So the moment the access to all the files is seamless, but the moment you access a file or try to write to a file in the image layer, what your overlay file system does is it moves it to the container layer. It copies it to container layer and makes all the edits in the container layer. Okay. So that once you remove this container, once the container goes, what is remaining? The image layer only. Okay. So this explains the behavior that when you created a file, right, and you killed the container, the file went away. That's because this layer goes off. That's what happens. And what remains when you start the new container is only the image. That's all I know, right? That's what I have. So it builds a new container layer which does not have anything currently, essentially. As and when you start editing the files, it will keep moving to the upper layer or the container or the working layer. So the files in the container layer are dominant and they obscure the existence of the same files in the image layer. Okay. And the container mount presents the unified view. So to create a container, this overlay driver, it combines the directory presenting the image's top layer plus a new directory layer for the container. So this is the lower dir in the overlay and is read only, and the new directory for the container is the upper dir. Okay. So so let's look at this in action. Okay. So now let's go into this. Oops. Okay. Let's go into my container layer and let's log into the one of the containers. Okay. So now let us look at these files. So if you remember, okay. So now let me touch a file. Let me see what I can do. Hmm. Okay, let's get into this file. Oh, okay. Let's get into, let's say, the one with this. Okay, so now let us take this etc host. You all know what this etc host is, right? So let's just copy this and paste this and we'll create a dummy commit. So I've done some minor edit. Okay. So this is what I have done. So let me take this. So what am I doing now? I am taking one of the files that come with the host, I mean the image layer, and I'm editing that. So now let's go out of this and let's try to find this container. Okay. So you have overlay 2 and you can see BCDC. Uh, 3BDC. Which is this? Just to find out what is the container, let me touch another file with this instead of bash. I will just say touch slash emp slash test. Okay. Now I'll find this file test. So now I know which is the one that has temp test. Okay. This is the one. So I will get into this container. Oops. This is the container, right? Let me get into this directory and let us look for etc host. So you can see, right, there is one in merged. So if you see, oops. Okay, this one is empty. This is interesting. So that means we have to find the right host. So you can see there is a resolve.conf here. Hmm. So let us try with this file. Okay, there's a sysctl.conf. And now let us get into this. Let's get into this. We have the sysctl.conf, right? We'll just go here and we'll just add some. Okay. Now let us go back here and go to our host and mm, you can see, right? Now there are two files here. You can get into this directory or we can do a cat of this. And you can see, right? This one has overlay fs and let's see what is in diff. Okay, this one also has that. This is interesting. And this should be in the base layer. Find dot minus name ctl dot conf. So we can do a Docker images, and we can see someone started. Yeah, I think if you do a cat of this, here, oops, yeah. So this is what happens when your container is starting. It is starting up and it is overriding all the files here. So that's probably why you are not able to see that. But essentially that is how your overlay file system works. When you create these files, it will use these diff and merged directory structures to maintain and track how the changes are happening across your container lifecycle. Okay. And when your container is killed, let us say docker rm minus f. One second, huh? One second. Okay, so let us remove this one that we started on the one with vi, and now if you go and check this, try to look for this. I think these two directories will be gone. Okay, so if you go to, and if you look at cd overlay 2 and ls, you'll see that this one is not there. The one with yeah, this directory is not there. You will not find it. Okay. If you say this, you will not find it here, right? Because the file is removed. So if you try to find sysctl.conf, basically you will see that it has removed those directories. Okay. So that's how the overlay file system and the container lifecycle essentially works. Questions here? Okay. So a few additional notes. So we discussed many of these, just collating the thoughts here. So Docker file system provides a writable container layer. So there's no static path. You saw, right? Every time a new container is generated, there is a new path generated. So when there is no container, there is no data. Okay, on the Docker file system, and it's as we saw, it's tightly coupled to the host machine. And earlier, it would use union file system, which is very similar to overlay, but it was of you know slower performance. So that's why later versions of Docker adopt the overlay file system. So with that, let's move to the different types of Docker mount. So there are three types of Docker mount. So there's a bind mount, there's a volume mount, and there is a tempfs mount. So bind mount typically and the volume mount, they are binding your file system's storage to the existing file system on the disk of their host. Whereas volume or a tempfs mount mounts data into your memory. So why would you require this? Because this will be your proc file system, those kind of things, they get mounted on the memory. They are in memory file systems, right? So you can see that what is the difference between a bind mount and a volume mount means when you bind mount a directory from a host to a container, the file that you access is directly from the file system path of the host. Whereas when you create a volume, the volume is created in the Docker area of your file system, which is we saw, right? Var lib Docker, right? this directory. You can see here, right? Var lib docker. This is your Docker area. This is this area that they are talking about. And these volumes will get created inside the var lib directory. So let's analyze each one of these types and play around with them a bit. Now, Docker volumes are essentially, you can see, right? They get created in the Docker area. They are created and typically managed by the Docker. So you have to create explicitly during this thing, or they can get implicitly created as anonymous volumes. So when you create it explicitly, it becomes a named volume. When Docker creates a volume for you because you did not specify the name, it becomes anonymous volume. It supports different type of volumes drivers, and you can essentially clean it up. Okay. So when do we use these volumes? So typically volumes allow you persistency of data across a container lifecycle, and it allows you sharing of data across two containers. For example, you can share data across two Nginx. Nginx, your simple web server, load balancer, proxy kind of an application. So you can store data across two such containers, for example, or you could store data across two different containers of your application if you have created. If you create a config volume, and if you have your database container, and if you have your application container, both of which are accessing your config files from that config volume, they can share that config. So essentially, it is a decoupled host and container file system architecture, basically meaning that it is not related to the host file system, and it is storing data outside of the host. You can mount your Docker area on a different disk, or central storage, or on a cloud storage, or on your EC2 storage or something, and then you can store this data out on top of that. Then it becomes easier. So it is also easier to backup and restore your Docker application lifecycle data if they are stored on volumes. Okay. So the next one is what we call bind mount. So bind mount is, let's see if we have the examples. Should we go through and see examples, or okay? Yeah, we can look at the examples later. So let's uh, yeah, I have it in the notes here. So let us look at the volume mount first. Okay. So what we can do is we can play around with a simple web server application. We can say Docker volume create. Okay. And then we'll say web server volume. Okay. So now we'll say Docker volume ls. You can see, right? It has a bunch of volumes. This was created in a previous exercise, and this is the one that we recently created. Okay. Now what happens? Let's try to run a Nginx container with this particular volume. So let's try to run this. We'll just say docker run and minus d minus name. We'll call it web server 1. Now you see I'm giving a name to my container. Okay. And then we'll say minus p. I'm making a port mapping. I'm running this container on port 80. Port 80 is the default HTTP port on any host. So when that web server application runs on that container, it will run it on port 80. But port 80, there's only one port 80 on the host, so it cannot map to port 80. So we will map it to port 3000. Okay. And now we will mount, and we'll say this is a command to mount the volume that we just created. We'll just say source is equal to ws dash wall, and then we'll say target is equal to slash user share nginx slash html. Now, why am I putting this? Because this is the directory which stores your index.html and your default HTML files that are painted in the browser when you access this web server. Okay. So I'm mounting that on the volume and I will say nginx. Okay. Now nginx is the container that I'm running based on that. So now it is telling me it's not able to, oops, not mount. Sorry, we missed a minus here. So we'll run it with this mount. And now you can see that there is a nginx command running. Docker ps minus a. You can see, right? There is a nginx command running. So let me clean this up. Let me clean up the older Ubuntu one. Uh, are you guys with me so far? So what we have done now is we have created a nginx simple web server command. And now you can see that name is whatever I gave here in the minus minus name option. Okay. And it is telling you that the port mapping on this host is this IP address of this host, which is 134.209. Ooh. Okay. If you're not talking, can you go on mute, please? Think someone is not on mute. Okay. Yeah. So now you see this is running. How do I know this is running? So now what I'll do is I'll take this IP address. I'll just open a browser window. Okay. I'll open a browser window and I'll take this IP address, which is 134.209, 146 and 37. Say 134. 209. Yeah, you can see, right? And the port is we added was 3000. And if you will see that your Nginx server is running here. Okay, can you see this? So now we'll try to find this volume here. We'll just say Docker volume inspect ws dot vol. You can see, right? It is telling me. What is this? This is telling me details about this particular volume. Again, I'm using the inspect command. So this is the beauty of Docker world. And I remember this is the consistency with which you are approaching your user flows, user workflows. So you have all these resources that you're creating. It could be containers, images, network, different types of networks. It could be volumes. It could be anything that you create. If you want details of that, you use the inspect command. So now it is telling me that the mount point is this. Okay. So let's go into the var lib docker and volumes directory. Now you can see my volume, right? WS vol. So now you will see underscore data. You will see index.html here. And I also have a ramaya.html. Okay. So let's see what is in index.html. And this is what you see here. This is what you saw in this page. Correct? So now we can just say, we can just try simply edit this and see what happens. Let's edit this. Okay. And if you refresh this, then you will see that it is showing up here. Correct? This is how easy it is. So now we'll do something slightly different than what we did earlier. We'll just kill this container. Okay. Okay. Now we'll just kill this container, and this should not load. Okay. So now you see it is not able to find this page. Okay. It's telling me unable to connect. So what we'll do now is we'll run it as web server 2. Okay. We use this command to run this. Instead of web server 1, we'll give it as web server 2, but we will mount the same volume. Okay. Now let's see what happens. If I do a refresh, and there you see. So this is unlike our earlier exercise where we had created, for example, VI, and what happened was when you killed the container and launched it again, that VI was gone, the file was gone. So what did we do here? In this case, we ran this container as instance web service 1. We created this, it created this file here. And when this container exited, this volume was not deleted because it is created as a separate resource. It is not the ephemeral or the short-lived container, default container storage. So I have mounted this specifically on a volume. So now I have all this data. Okay. So now, clear with me so far? So this is your bind mount, rather, sorry. This is your volume mount. So when you see the volume mount will be here. Okay. So these are the volumes. Okay. So now let us move to bind mount. So let us look at bind mount, for example. We discussed this thing. So now let us look at bind mounts. So we discussed what is a volume mount. Now let's try to use a bind mount. Now bind mount is basically the file system is now maintained by the host. It's on the host file system area. Okay. So obviously the problem with this is your containers mostly run as non-privileged users. So if they have access to these files, they can make changes and they can cause security implications, which is a violation of one of the isolation criteria we discussed earlier. We discussed earlier, right? When we started with the foundations of the Docker, when we analyzed a bit of history, we saw that the security implications or issues are that you are writing into the disk space of some other process. You are accessing, areas of the disk space which you are not supposed to access. So bind mounts allows you to break that, but in a more structured way. So why is this required? We'll discuss that. What are the use cases? So essentially, because there is no Docker that is interfering every time you do a read or a write, it is directly writing to the host file system. It will be obviously more performant. There is one less abstraction layer. And basically, it requires to have specific directory structures on the host. So we'll try out some examples. We'll get there. What are the use cases of bind mounts? So here, basically, when you're sharing config from the host, that is one of the primary use cases. Like for example, you have your your DNS configuration, which is in your etc resolve.conf, or your host etc host, the set of local LAN hosts that you can access without hitting your DNS or routers or all those configurations that are in your etc host files can be shared along with using the bound line. Now, typically, another use case is DevOps build lifecycle. Now, how many are familiar with the term DevOps? Have you guys heard of this term, DevOps? DevOps is basically they are the it's a process or the team that takes care of your product build, deployment, test life cycles, and automation of that. Okay, so what we do when we build projects is you will have a target directory. For example, you will have your code in your Git repositories, and when you build your code, all the for example, if you're doing a Java project, all the class files will go into the target directory. From where they will be you know combined as a jar file, and then your jar files exist in specific target folders. And when you have a DevOps pipeline, what happens is there is one container that generates the build and then hands it off to the next steps, which is another container which takes and packages this nicely as some installer, as some RPM, or as a MSI install package or something like that. So there, if you put it on a target directory, then you will know that your build container is the producer of the data inside the target container, and your packaging container consumes that data from the target folder. Okay, so you can use this to as a similar mechanism to share data across two different running containers as well. So let's try out some examples of bind mounts. Okay, so now what we'll do, so we'll make a web directory. So let's see if this is already created. Uh, okay, so we'll say, okay, we'll create this directory. Okay, so now we will, now we have this desktop, and you have inside desktop, you have this web server directory. Now let's bind mount this directory to our Nginx. Okay, so we'll do the same command, docker run -d, and we'll give it as name as web server 3, for example, and then bind it to a different port this time. Let's say 3001, and it's running 80. And then we'll give the mount, we'll give the type as bind mount, and then source as this directory, right? Slash root slash desktop slash ws dash dir, and then target as the same, slash user slash share slash linux slash html. Okay, and then we will run the nginx thing. So now you will see that there are two nginx web servers, ws web server 2, and I have a ws3. WS3 is running on port 3001. So I can go here, right? And I can change it to 3001. Oh, interesting. Why is it forbidden? Okay. So now, is it okay? I don't think there's anything inside this. There's nothing inside this. That's why it's not able to do this. So let's just try to create a simple file. Let's say we'll do it as msrit.html, right? So now we'll just create some simple content in this. Okay, I'll just copy paste it from somewhere else. I'll just say HTML, or we'll just write it, write HTML tag, and we'll say title is bind mount demo. Okay, and then we'll say body. This simple HTML, right? Okay, just create the body and then I'll close the HTML tag. Okay, this is a simple HTML. So now what I'll do, I'll go here and instead of this, just say now you saw, right? So what did I do? I went to the host and from the host, I edited in this directory, which is root desktop web server directory. And then you can see that we started it as a bind mount. Now, if you want to see this, you do a Docker inspect on this container and you will see what is the mount type here. You can see, right? You will see what are the mounts that are available. So you can see, right? You can see the mount is of type bound and the directory is this and the destination is HTML. And why does this work? Because typically what happens is when when your Nginx starts, it looks for the default directory inside the Nginx is user share Nginx HTML. Okay. So now let us say if I copy this as index.html. Now if you saw right earlier this was coming as forbidden. Now it will load the same thing. How do I know it is loading the same thing? Let's just edit this to make this different. Uh, let's just say, okay, let's just say this. And then you can see here, right? So typically what happens is when your web server from the default directory, when it loads, if you list a directory or if you don't specify what to load, just specify the server name, it tries to load index.html. This is standard web server behavior. Now, where is it looking for index.html? This is the mount directory, user share nginx HTML. That's where nginx looks at for. So I created this index.html, it loaded. When I remove this, you will get a forbidden error because there is nothing and you cannot list a directory. Okay, when you try to list a directory, the web server tries to load the index.html inside the directory. This is a web server behavior. Okay, so this is your bind mount. Let's look at tempfs. Now we can do a tempfs example. It will be more or less the same, but typically it will be this thing. Okay, so it's only loaded in memory. Okay, it's not in the file system area, and it is typically works for storing sensitive data, and obviously it's extremely fast and There is no cleanup that is needed afterwards because it is on TempFS. Now, where does this work? It essentially works in IO sensitive projects where you have to have IO running very fast, and it just, you know, typically with works on standalone containers, which with actually with no need actually. This is not with need. It doesn't work with no need. Okay, this is a read only. That's fine. We'll edit that later. That's a mistake. It doesn't work with this thing. Okay, so that's your TempFS bind. We can we can try the examples for TempFS and conclude for the day. So I do the same. So now what I'll do is I'll run this docker run minus d minus minus. Let's do the, okay, we'll do the same. We'll call it ws4. We'll call the type the bind as tmpfs. Okay, and then there is no source because tempfs is on the memory. So the target will be the same, and we'll run the nginx here. Okay, never failed. I don't think. Okay, that's because 3001 is already allocated. Let's call it 3002. Okay. Is there a problem? Is already used by container. Okay. So let's do some cleanup. And it was not able to start it, but it created. See, it is not in a running state, it is in a created state. So let us remove this web server. Okay. Now run this again. It should be able to create. So you can see there is WS4. And now we can try port. What is the port? 3002, right? And again, you will see forbidden. And there's no file here. So what I have to do is I have to log into the container, docker exec minus it ws4 bash. Okay. And I can say index, get into user, share, Nginx HTML. You can see there are no files here. So I'll just do a echo of my this thing and just write some HTML, right? Demo, just say temp fs demo, and then we'll say body. I'm just typing this HTML. Hello, welcome to tempfs mount demo. Okay. And then okay, just type it to index.html. Okay, so now you can see here what happened here. You can see, right? So now here, this is mounted on tempfs. Let's try to find this. So let's delete the other two. WS3 and web server 2. Okay. Ooh, this is done. So we'll go to var lib docker and we'll find, let's try to find where is index.html. Okay, so you can see there is one each in the volume that we created, and there is one in the normal container area. So now if I delete, if I remove ws4, this should also go away. Okay, which is this one. And you see, this is the default. This is coming from the image, Nginx image. This is not the HTML that I did with the echo. So essentially, what this is showing you is that tempfs is basically a temporary file system mount. It just allows you to access the files in a certain way. That's all. Okay, it's has very limited applications, and typically we don't use it. It's just more of academic interest, but it's not generally used in most of the type of applications that we develop. Okay, so that kind of brings us to the end of this. So if you want to see more details, you can look into this. You can copy this link. Sorry, you can go to docs.docker.com/storage, and you can access all the details here. Okay, the different types. We didn't cover named pipes. They're slightly more complex, but we'll leave it for now. You can read through these details here. Okay, let me paste this link in the this thing. Okay, that's all I had for today's class. Are there any questions? So, quick recap for today's class. We try to understand how overlay file system works in Docker, how the image layer is mapped to the read-only layer, and how the Docker creates a container writable layer and uses it to implement your Docker file system. And we looked at the different type of storage configurations. We looked at volume mounts. We looked at bind mounts, and we looked at tempfs mounts. And just quickly cover name pipe for academic interest, but they can be used for, yeah, name pipes are typically, it's like pipes are conduits of communication, data communication. Essentially here they can be used as between the host and a container. Typically we don't use it, but yeah, so you can go to this, learn more about volume, bind, and tempfs. You can read these structures. There'll be more data about when to use volumes. Each of those will be present here. Okay. So more or less, I have tried to encapsulate that in my presentations. You can go through here. I will share the presentations with your more details. Okay. This is exactly how we derived the exercise from. Are there any questions? If there are no questions, I'm done for the day. Shilpa madam, I think we need to cover one more topic. I'll need 1 more hour. So I will try to see. I'll work with you and Chandrika ma'am to schedule 1 hour next week, 1 or 1.5
Yeah.
hours next week, and or maybe 2 hours, and we can cover the remaining topic. And if the students have any questions, we can cover that. Or if they don't have questions, if they are interested, I can I can show them something else, some other things other than what is there in the syllabus in the Docker world. Okay.
Yeah.
Okay. Thank you very much. If you have any questions, feel free to reach out to me. I'll post my phone number here. So I feel free to reach out to me on WhatsApp. Make sure you give a proper introduction so that I don't block your number. Feel free to reach out to me. I have shared my phone number on the chat. You can reach out to me or you can email me at this email ID. So I'll try to get back to you with questions. Obviously, reaching out to my phone will be faster. So if you have any questions, don't hesitate to reach out. If you are trying to do some projects, and if you need some help on how to containerize them, we can discuss that as well. So we'll meet next week and we'll close the final chapter and finish this topic. Okay. Thank you very much. Have a nice evening, everyone.
Thank you. Yeah.
Thank you. Bye bye.